So thank you for the invitation to speak at the Physics and Astronomy Club. And also thank you to Sumit, who was the first person who got in touch with me. I understand he's indisposed at the moment. So let me share my slides. I'll share my screen and get on with the talk.
Also, sir, we are starting the live streaming of the video and we are recording the
Yes.
meeting.
Fine, fine. That's okay.
Thank you, sir. You may proceed.
So can you see my slides?
Yes, sir. Your slides are visible.
Okay. So let me start. The title of my talk is Space, Time, and Disorder. And on the first slide, you can see two objects, which you've definitely seen before. On the left, what you see is a steam engine. And what the steam engine does is it converts heat into directed motion. If a train wants to get from A to B, say from Delhi to Jaisalmer, it has to move in a directed fashion. But the source of energy for this motion is actually disordered. It consists of heat, which is undirected motion at a microscopic level. On the right, what you see is a black hole. And a black hole is something which we find in our galaxy, for example, and many other galaxies around the universe. Astronomers have been studying them for decades. A black hole is basically a light trap, something whose gravity will not permit light to escape from it. It has some remarkable properties, and it's at the edge of theoretical physics at the moment. Many of the problems that we have in fundamental physics stems from a failure to understand black holes properly, from a fundamental theoretical physics point of view. So what I will be doing is to go through my talk in a rapid succession. I will not... I will actually pause for questions at discrete points. So if you have a question which cannot wait until the pause, please ask it directly. Otherwise, you can wait for the question mark to come on the screen and ask your question at that time. I'm hoping to combine, by this method, I hope to combine giving a straight talk without questions with actually being interrupted by questions, but not in a way that derails the talk. So the plan of the talk is as follows. I'll speak for about 15 minutes, a long introduction. Then talk about relativity for 10 minutes, black holes for 10 minutes. And the main theme of my talk is order and disorder. And then I'll convince you that black holes are warm objects. That is, they're not cold. They're not ice-cold objects. Neither are they super hot, but they're somewhere in between. They're warm. And a brief conclusion. I want to thank some of the help I got from some of the students at CMI, where I'd given this talk in person. And at that time, they helped me convert many of the demos I had into videos. And that's useful for giving an online talk. That's what I'm using today. So the whole idea is that I'm going to be extremely non-mathematical. That is to say, the subject is basically a mathematical one, but there's also a lot of physics in it. And I'm trying to bring the physics to the forefront. So I will use almost no equations. I'll just use two equations, one of which you've definitely seen before. That is E equal to mc squared. And the other, which you probably have seen before, that the energy of a photon is given by Planck's constant times the frequency. So apart from using words, which I'm going to talk about, I'm going to use pictures and demos. Demos have a way of bringing to life the point I'm trying to make. Unfortunately, because it's an online talk, I can't show you the demos in live form, but I've made videos of them with the help from the friends at Chennai Mathematical Institute. I'm also going to use analogies in order to put the main points across. And I also apologize to people who wanted much more in terms of mathematics. This is going to be an elementary talk, and elementary talks will elicit elementary questions that they're most welcome. Please ask them if you feel that you are not following the talk. So let me start with the speed of light. Light is probably the fastest thing that you must have encountered. It travels around the Earth 7 times in a second. We've all been told that the speed of light is very large, and it's true. It just takes 1.5 seconds to get to the moon, whereas the spacecraft takes days to get there. But in a sense, the speed of light is also very slow. It may be very fast from the point of view of velocities that we are used to in everyday life. But at a cosmological scale, you will also appreciate that the speed of light is very large. In that sense, I'm going to contradict myself. Light takes 8 minutes to get to the sun, 10 hours to Pluto, 4.5 years to the nearest star, 3 million years to Andromeda, the nearest galaxy. And there are galaxies that you can see where the light took billions of years to reach us. And these galaxies emitted the light that we see today at the time when dinosaurs were on the Earth. There are some galaxies of that kind. The further out you look into space you look, the deeper into the past you're looking. So the subject of cosmology resembles archaeology in many ways. We're digging into the past to find out more about the universe in its early stages. Relativity acknowledges the finiteness of the speed of light and also its universality. The fact that everybody measures the same value for the speed of light. And when I use analogies, what I'm trying to do is to relate new things to familiar ones. I believe it was Picasso who said that if you want to explain something new to somebody, what you have to do is to mix it with something old. Analogies serve a very useful purpose. The analogy is something that takes A and compares it to B. You already understand B better, and you have a hope of understanding B. And they're never perfect, but they're almost always useful. Similes, metaphors, these are all devices used by poets, doctors, and lawyers, and investment bankers. So the first analogy I'm going to bring up is that sound is very much like light. Both are waves, both travel at a finite speed. Both have vibrations at a certain frequency. And the pitch of sound is like the color of light. Of course, there are differences. Sound needs air or a medium to travel, whereas light can travel in vacuum, in empty space. If you see thunder and lightning, the flash of lightning reaches you much faster than the sound, the sound of the thunder that you hear. That's because light travels much faster than light. Those are all differences which are superficial. The more deeper question, the deeper analogy is that they're both waves, they both have a finite speed. Now you can have sources of sound, so thunder, voices, annoying horns, or musical instruments, or a flute. The sources of light are lightning, tube lights, the sun, disturbed atoms. Atoms emit certain frequencies, and this is an atomic fingerprint. Each atom has its own special set of frequencies. And I'm going to demonstrate this with my first 2 demos. Let me start with showing you what a slinky does. And I'll turn the camera slightly so you can see the demo. Yeah, I don't know if you can see this. I'm setting up a fundamental vibration with the slinky. Is it audible? Is it visible? Can you see the slinky vibrating?
Yes, sir, the audience can see it.
You can see it, okay. So now I'm going to vibrate with a higher frequency. You'll notice now that it's vibrating at a higher frequency. So this is the generic feature of waves which are confined. So in an atom, you have electron waves which are sloshing around in the potential of the nucleus. And because the nucleus provides a box for the waves to move in, the waves come at certain definite frequencies. So is that point clear?
Yes, sir. It was clear to the audience.
Yeah. Okay, so let me show you one more demonstration. I'm going to take a tube and fill it with water. Okay, this is a little messy. Let me get a different demo here. Yeah, instead of the water demo, I'm going to choose a different thing. This is a flute, which produces a note like this. You notice that I didn't move my fingers. I kept my fingers closed and I produced 4 different frequencies. These are the fundamental plus overtones. And just like the flute has a fundamental plus overtones, an atom has a lowest frequency and also higher frequencies that you can see from an atom. And that constitutes the spectrum of the atom, just like you have a spectrum for the flute.
So your audio
I'm
isn't.
sorry,
We can't. The flute isn't audible, sir.
it's not audible. Okay. Okay, now?
Yes, sir. No, sir. Right now it isn't audible. The flute.
It's the frequency is too high, but I'm playing several different pitches on this with the same flute, with the same fingering also. So the basic point is simply that if you have a sound wave, it consists of a fundamental plus higher harmonics. And in the same way, an atom also, and the slinky has a fundamental plus higher harmonics. Okay? So let me go on. Yeah, the demos don't work so well on the internet, I guess. Okay. Now, so I'm going to show you.
This method that I just described. There are several ways in which you can perform this. Usually I do it soaking the splint in a solution of ethanol for some hours. And then I dip the splint in the powder. So this one is copper chloride. These are moving the flame. Wow. Oh my goodness.
Okay, so that was a demonstration of the spectrum of atoms. It's the flame test which is used in chemistry in order to get the atomic spectra. And light from moving sources is shifted in frequency. And if you have an atom at a distant part of the universe, because the universe is expanding, you can find a shift in the frequency, and that's called the Doppler shift. So in the same way that sound has a Doppler shift, light also has a Doppler shift. And this is the cosmological redshift that was detected by Hubble in the 1920s. So the speed of light, I told you, is nature's speed limit. Nothing can go faster than light. If we disregard the speed limit as being large, we'll end up with Newtonian physics. If we acknowledge the speed limit, then we have Einsteinian physics, and that's what you need in order to understand the universe in a large scale. That's the cosmological scale. Most of this talk we will stay in Newtonian, but I will use finite value of c. Now, just as atoms emit photons, which are particles of light, sound waves are produced and they are phonons, and the energy of photons is proportional to the frequency of light. And I've been through this already in this cartoon, where E equal to h nu. So any questions on the introduction? Please ask them now.
If anyone from the audience has any doubt, feel free to come up here and talk to the prof. No, sir. So far, there are no doubts.
Okay. So there's a close relation between relativity and geometry. Space-time is the set of all events. That is to say, all events that take place. For example, let's say that we'll take some firecracker bursting at Diwali. That's an event. That's characterized by location in space and in time. So, for example, the firecracker might have gone in your garden, might have been burst in your garden at a particular date and time. So if we take the set of all events, that is what we call space-time. It's impossible to precisely define what you mean by an event, just as you can't define what you mean by a point in geometry. Normally, time is measured in seconds and space in meters or centimeters. We can use the speed of light to convert all measurements into seconds. We can measure space in seconds by asking how long does it take for light to get from A to B. Or you can measure time in meters by converting everything into units of distance. Multiply time by speed of light and you get distance. This is a consistent worldview in which we equate space and time together. And that's the basic idea of geometry. In special relativity, we get from space to space-time. That is, the union of space and time together is what we call space-time. It's four-dimensional. And in general relativity, which is the theory of gravitation, we get from flat space-time to curved space-time. And a picture of curved space-time looks something like this. Here is space-time, and you plot time on the y-axis and space on the x-axis. It's only two dimensions I'm drawing here. So this is an example of a straight line. This is an example of a curved line. And this is an example of a line that's piecewise straight. Now we are in the realm of geometry. We think of space-time geometry, and that's what we do in relativity. In relativity, gravity is described by a curved space-time in which small pieces appear like the space-time of special relativity. By piecing together small flat tiles, we can produce a curved space. Bodies follow the local straight lines, but because space-time is curved, they appear to curve. And if you've seen a globe, you'll know what I mean. The surface of a globe is curved. And you can also understand curved space-time by using the piece of paper which I've asked Rupa to distribute. Please take a look at those pieces of paper. If you join them together, you'll find that you have a cone. Have you got the pieces of paper?
Yes, sir. We have distributed the papers.
Yeah. So take the papers and you follow the instructions of the papers and you make the lines join so that the piece of paper is folded into a cone. First start with the 3/4 piece of paper and just make a cone out of it. So when you do that, you'll notice that you have a triangle in which all the angles are right angles. So can you see that? Yeah.
Sir, they are folding it right now.
Okay, okay.
So every bench has at least one set of each of the two papers.
Yeah.
In case anyone doesn't have it, you can share with your neighbors.
Yeah, you take the three-quarter paper and fold it so it's like cone, like a ice cream cone or something. And you'll see that there's a picture on the paper which describes a triangle with three right angles. All three angles are right angles. So that's an example of curvature. The sum of the angles of a triangle on a plane, which is flat, always equals 180 degrees. But here you'll see that the sum of the angles is 270 degrees. This can happen on a globe, for example, or it can happen on a cone, which is what you're looking at. Okay. Now, if you take the other piece of paper, the full piece of paper, you can fold that also into a cone. And you'll see that between two lines, A and B, between 2 points A and B, you have two different straight lines passing through them. Can you do that? Can you see that?
Yes, sir, the audience are.
Yeah. So this also happens on a globe. If you take 2 points opposite
Uh,
points here.
Sir, do you have these sheets with you so that you can demonstrate from
Sure,
your
sure.
side?
I'll bring the sheets into.
Okay, sure, sir.
Yes. Here's a three-quarter sheet of paper. So what I do is I just fold it so that the O's join together. Then what you see is that there's a triangle. And each of the angles of the triangle is a right angle. Like this one is a right angle. This is a right angle. And that's a right angle. Right? That's a demonstration of curvature and what we mean by curvature. If you take the other sheet, this is a full sheet of paper, and I fold it so that the O's join together. Then you can see that between the 2 points, there are two straight lines. The points A and B are joined by two different straight lines. This never happens on the plane. So for example, in a curved geometry, you can have two rays of light that start from one point and focus again together. That's what Einstein's theory says, just like I showed you on the piece of paper. So Einstein's theory is basically saying that space-time is locally flat, just like the globe is locally flat. But when you put all the pieces together, you get something curved. Bodies follow the local straight lines, but because space-time is curved, we think that they're moving in lines which are not straight. I don't know if this point came across. So here's a picture of space-time as conceived by Einstein. You can see that right here, there's a hole there. That's probably a black hole or something. And everywhere outside, the space-time is curved. Now, why did Einstein propose this idea? And it has to do with acceleration and gravity being the same thing. Gravity can be eliminated by yielding to it. So in a sense, there is no gravity. If you're in free fall, there is no gravity. You might have seen space walking. People who are falling into space, they don't sense any kind of gravity. Gravity can be simulated by acceleration and eliminated by falling with it. And since it has been shown that all bodies fall in the same way in a gravitational field, the path that they follow is not a property of the body, but a property of the space-time. By using this trick, Einstein was able to eliminate gravity. Now, let me show you a demo, which I've made a video of. So the demo consists of dropping a water bottle in which there are two holes on either side. If I keep a bottle of water with holes in it, water is going to leak out. And you'll see this leaking out initially. And this is a slow motion picture, so you can see very clearly what happens when the bottle is dropped. So when the bottle is not falling, you see that the water is leaking out of the bottle. When it starts falling, the water stops leaking instantly. And when it hits the ground, of course, there is a big rush of water again.
Yeah.
Did you see that?
Yes, sir.
In the falling bottle, there was no water leaking out of the bottle. Shall I show it once more?
Sure, sir. You can show it once more.
Yeah.
Okay, that was one demo. Here's another demo, which, okay, I'll skip this one. It's a very similar thing to the earlier one. Yes. Here it is a little clearer, perhaps. Now, the idea behind Einstein's theory is that when you say space-time is curved, you can have the following kind of situation. You have a parallelogram, and normally in a flat space, the parallelogram has got opposite sides equal to each other. Here's an example of a parallelogram which comes up in a curved space where the two sides have different lengths. The opposite sides have different lengths. This can happen with curvature. And you can see that by drawing a parallelogram on a sphere, if you like. So any questions about what I said?
Yes, sir. There is one question.
Yes.
You may please come up here. You can stick your notes on it as good.
Hello, sir.
Yes, please.
My name is Vijay Kendri from Structural Dynamics, Perkuik
Yes.
Department. As you have told, the relationship between space and time is curved. But while presenting that one, you have told that we are converting space into the time domain by
Yes.
considering speed of the light as a constant.
Yes.
So, if I considering distance equal to speed of light into the time, considering distance as a variable, the time will also variable, and the speed of light will be the constant. So
Yes.
it will follow the equation y equal to mx, which is equal to the straight line. Then why you are considering as a space time as a curve?
Yeah. So you're absolutely right. In special relativity, we consider space-time to be flat.
Yeah.
Okay. So that's what you're saying is absolutely right. And all the bodies move in straight lines in the absence of gravity. If you go to outer space, far away from any gravitating body, space-time is actually flat. But when you come close to a gravitating body, you find that they follow trajectories which are not straight lines. Okay.
Oh.
To explain this, Einstein proposed that they are actually following straight lines, but in a curved manifold, in a curved space-time.
Oh.
And this theory has been extremely successful. It makes a lot of predictions about the universe, about the solar system, and even about laboratory physics, all of which have been verified. And most recently, the predictions of Einstein that gravitational waves exist and that they're emitted when two black holes collide with each other, that has also been verified. So this is a theory which has earned the trust of physicists all over the world. And it was
Sir.
proposed about 100 years ago actually more than 100 years ago. And so far, there's been no evidence to the contrary of the theory.
Sir, I'm get some part I'm still confused that you are explaining that Einstein has proposed some absolute relativity, deviating from a straight line equation to the curve line. But
Yes.
what he thinks that we have to go from we have to change the path from straight to the curve. So that means what is the thing behind that one? I want to ask that one. Main question is that.
So what he's proposing is that in the presence of gravitation, space-time is actually curved, and every particle follows a path which is locally straight. You know, in a curved space, like on the Earth is curved, we know that. But
Yeah.
when you build a house, you don't worry about the curvature of space, of the Earth. You just build a house. But in a small region, you can regard the space as flat, right?
Okay.
Like if you go into your garden, you won't see the curvature of the Earth. And if you plot a triangle there, you'll see that the sum of the angles is 180 degrees. So if
Yeah.
you use that logic, you'll find that you're actually following a straight line locally.
Yeah.
That's what the planets are doing in the gravitational field of the sun. Each planet is following a locally straight path. But if you look at the path globally, you find that it's actually curved and it looks like an ellipse.
Okay. Okay, sir. Thank you.
Yeah. So it's a very beautiful theory, and it actually explains a lot of facts that we have had.
Okay, sir. Okay, sir. Thank you.
For your question. Yeah. We now continue unless there are more questions.
Is there any more questions? No, sir, you may continue.
Okay. So black holes are basically traps of light. So there's the notion of escape velocity. If you want to shoot a stone into outer space from the Earth, you have to give it a certain minimum amount of energy. If you throw it up, like if I take this bottle cap and I just throw it up, it'll go up and it'll come down. But if I throw it with higher and higher speed, at some point, it can go so fast that it'll go off into space. And it doesn't matter if I throw it vertically upwards or sideways. If I give it enough energy, it can escape from the gravitational field of the Earth. But what if the gravitational field of the Earth is so strong that I have to throw it at the speed of light in order for it to escape? Then nothing can escape from the gravitational field of the Earth. That's what we call a black hole. And if I wanted to convert the Earth into a black hole, I have to squeeze it so tight that it becomes as small as this bottle cap. So the Earth, if compressed to the size of 1 centimeter, would become a black hole. The sun, if compressed to 3 kilometers, would become a
So your voice is breaking a
black
little.
hole. This idea was actually proposed gravity, called just
So your
independent of Michel.
audio is breaking.
And
Sir, am I audible?
on.
In the chat box that we are not able to hear you.
Yes, you're audible.
So your audio was breaking. Could you repeat what we just said?
Yeah. So I was talking about the notion of an escape velocity. Just a minute, I'll close the door. So I was talking about the notion of an escape velocity, the speed with which you have to throw an object in order for it to escape into outer space, to leave the gravitational field of the Earth. That escape velocity is about, say, 11 kilometers per second at the surface of the Earth. But if I were to compress the Earth into the size of this bottle cap, which is about 1 centimeter, then not even light will be able to escape from the Earth. This idea was given by Michel and Laplace quite a long time ago using just Newtonian gravity. But when Einstein put forward his theory, Schwarzschild discovered a solution which is now interpreted as that of a black hole. And the very distinguished astrophysicist Chandrasekhar in 1930 realized that stars can collapse into black holes. So it turns out that stars, when they use up their fuel, they start collapsing under their own gravity. Normally, it's the pressure of the heat with the star that keeps the star shining and alive. But once the nuclear fuel runs out, it starts compressing, getting smaller and smaller. And finally, it becomes a white dwarf, where it's the quantum mechanical effects of electrons' motion and the uncertainty principle that causes the stars to have some resistance to gravity, to have some internal pressure. But if the stars are massive enough, this pressure will not work and the star will collapse into a black hole. This was clearly understood by Chandrasekhar in the 1930s. But of course, the idea was not accepted widely until the 1960s. And then it became clear that there are black holes in the universe. Now, just after the war, after the Second World War, people had mastered radar technology. And after the war was over, they turned their telescopes, the radar equipment, into radio telescopes to look out into the universe and look at radio wave emission. And then they were surprised by what they found. They found that there were very energetic sources of energy. And black holes are not only traps of light, they're also very good sources of energy. The reason for that is that if you just take the argument of escape velocity and reverse it, you find that matter falling into a black hole will release an enormous amount of energy. Just as when you want to send an object to infinity, you have to put in an enormous amount of energy to make it escape to infinity. If you reverse the argument, you find that when it falls from infinity, it releases a huge amount of energy. So in the picture which I showed you earlier for a black hole, matter is falling into a black hole from a star. And as it falls in, it releases its energy, gets hotter and hotter, and puts out a huge amount of energy, 1,000 times the luminosity of our galaxy in a solar system size, which is just about one light day. Black holes are good sources of energy, and that's exactly what they were seeing, that there was a very violent events going on in the galaxy, releasing a huge amount of energy. So let me now show you what happens if you have a black hole falling. Now, if you have an object falling into a black hole and emitting a constant frequency. So I'll first play this clip, which shows what happens when an object emits a constant frequency. You'll hear it now. That's a rather annoying sound. But next, I'm going to show you what happens.
Sir,
if
your
the source-
slide is visible. No video is visible right now.
Sorry, no.
Right now, your black hole sources of energy, that slide is visible. Are you showing a video?
Okay. Audio. Just listen to the sound. Huh? All right. So this is
Uh,
the sound. It's a constant whine. Okay, next what I'm going to do is to take the same sound and tell you how it looks. If you throw the source of the sound into a black hole, you'll find that the sound gets Doppler shifted because of the gravitational redshift and also the Doppler shift. You find that the same sound appears like this when an object is falling into a black hole.
so, like no audio is visible. Like your voice is visible, but no other audio is visible. Sorry, audible.
Could you hear the audio?
No, sir, we can hear you speak, but no other audio.
Oh. Okay. So this is not working. So maybe I'll do it in a different way then. I'll
Okay.
give you an idea of what the sound looks like. Can you hear that? Can you hear that?
No, sir.
Okay, let me come here. So what I've got is a tube filled with water. Can you hear the sound?
No, sir. Your voice is audible, but not
Oh, but
the
I'm
other.
coming very close to the microphone. Can you hear that sound?
No, sir.
No? Amazing.
Like at the beginning, there was a slight sound, but
What's that? A whistling sound.
uh,
That's what I want you to hear. A whistling sound is what comes.
there was a slight whistling sound. Yes, sir.
Okay, okay. So maybe I have to get closer to the microphone. I'm not sure how to do that. Basically, the sound starts at a high frequency and starts coming down rapidly in frequency. Maybe I'll skip this demo. It's not working so well then. Yeah.
Yes, sir. I think that would be better.
Yeah, I don't know why the Mathematica file does not play. So I'll just go back to the. Now is the slides visible?
Yes, sir. Your slides are visible.
Okay, okay. So the reason you can use black holes as sources of energy is that the huge gravitational potential energy is released when you drop an object into a black hole. When you lower an object into a black hole, you can take this piece of matter here and lower it gently into a black hole and use a pulley to lift weights on Earth. Like that, we can extract all the energy of the mass into lifting water on Earth. And you can extract actually 100% of the energy of the MC squared energy of the matter by dropping it into a black hole, lowering it very gently, and then releasing it into the black hole. So this is a very ideal process where you can extract all the energy. But in fact, the efficiency of this process astrophysically is only about 5%. And that itself is a huge amount of energy because MC squared is a very large amount of energy that you release from even 1 gram of matter. Okay, I'll skip this slide because I'm not. Let me see. Yeah. So you might have seen the movie Interstellar, in which a black hole looks somewhat like this. You have an accretion disk. That's matter falling into the black hole. And what you see up on top of this thing and below are really the same flat disk. But because the light coming to you from the other side of the disk is curved by the gravitational field of the black hole, it appears to be above and also below. This is a picture of a black hole where you can see that the accretion disk is rotating in an anti-clockwise direction. And this part is very bright because the matter is coming towards you. All the photons are directed towards you. And that makes it look very bright over there. Now let's come to the the part of the talk which I want to emphasize the most. That has to do with heat engines. So let me ask you a question. Environmentalists tell you to conserve energy. Physicists will tell you that energy is conserved. So the question I'm about to ask you is, why do you need to conserve energy if energy is anyway conserved? Can anyone tell me an answer to that?
Anybody from the audience? Could you please come up here?
More efficient, more, more
Sorry?
efficient use of entropy, like it does, I don't know, entropy, like we have to you like it's always gonna increase, but like more amount of work is done for
Yes.
efficiently.
Yeah, absolutely right. So the fact is that energy is conserved. That's true. But energy comes in two kinds. One kind of energy is, for example, electrical energy or potential energy or kinetic energy. Another kind of energy is heat. And the difference between these two is entropy, in the sense that the heat energy is disordered motion, whereas the other energies are either potential energy or ordered motion. So when we say we are wasting energy, what we mean is that we are converting ordered motion into disordered motion, or converting potential energy into heat. So heat is basically wasted energy. So you cannot suppose you have a closed system in which there is some energy, and what you find is that with time, it becomes more and more disordered. So energy is constantly being wasted by being converted into heat. When all the energy is converted into heat, that object has a temperature. And if you have a single temperature, you cannot convert that heat into any kind of directed motion. So energy is conserved, but it can be wasted. And a similar thing is true for money also. Money is conserved in the sense that you cannot create money or you cannot destroy money. I mean, it's against the law to destroy money. If you light a 100 rupee note, apparently there's a law against it. And you cannot print 100 rupee notes in your basement. There's a law against that too. So, like energy, money cannot be created or destroyed, but you can waste money. You can go and buy useless things with it. For example, many people trying to get fit, they buy an exercise machine and they don't use it. That's a waste of money, right? And if you want to sell that machine, you will not get back what you paid for it. In the same way, heat cannot be completely converted into energy, can only be partially converted. And I'll show you, if you want to convert heat, undirected motion, into directed motion, you must have at least two different temperatures. That's the principle of a heat engine. And many of you who study engineering will realize, for example, that thermodynamics is an important part of physics, that heat can only be partially converted into directed motion. Heat is a degraded form of energy, disordered molecular motion. You can convert electrical energy to light, as you can see in the bulb which is above me, kinetic to potential. The first law of thermodynamics tells you that energy is conserved. The second law of thermodynamics tells you that you cannot completely convert heat into work. Energy is conserved, but it can be wasted. Converting ordered motion into disordered motion is a waste of energy. And I'll show you now, by means of a simple demo. Entropy is a measure of the disorder which is in a system. For example, if a set of particles is all moving in the same direction, it's ordered motion. Whereas if they're moving in different directions, that's disordered motion. And the second law of thermodynamics tells you that entropy always increases for a closed system. To appreciate the difference, the relation between disordered and heat, I'd ask you to take up the rubber bands, which Rupa has distributed.
Yes, sir, we are distributing rubber bands.
Yeah, so each of you has the rubber band. Here's the rubber band.
Sir, could you give us 2 minutes? We are distributing the rubber bands right now.
Okay.
Does everyone have a rubber band with you? If not, you can collect it from the volunteer. Ji. Please
So,
raise your hands if you don't have a rubber band, and she'll be coming to you. Uh, yes, sir. So you can continue.
yeah, so the people who have rubber bands, you just hold it like this in front of you. And if you pull it tight, you'll see that it gets stretched out. Now, when it gets stretched out, rubber is a polymer and it has a lot of molecules which are quite long. When you pull the rubber band, all the molecules get stretched out and they become all straight. So the stretched out configuration has got a lot of order, and the contracted configuration has got a lot of disorder because the molecules are going all in different directions. But when you pull it out like this, the molecules are all straight and parallel to each other. That is order, this is disorder. So to appreciate the connection between disorder and heat, you can do the following experiment. If I pull it out like this and suddenly relax it, put it on your forehead, you'll find that when you pull it, your forehead feels hot. When you release it, your forehead feels cold. Just try it out and tell me if you agree with that. Pull it rapidly and you'll find that the forehead is hot. Release it rapidly, you find your forehead is slightly colder. That is, you'll feel cold, as if the rubber band is cooled down. So the entropy being thrown out of the system is what's causing the heat. Here you can see a direct connection between entropy and heat. Does anybody agree with that?
Yes, sir, everyone agrees.
No, I'd like somebody from the audience can confirm that they actually. Okay, good.
Sir, are the audience audible to you?
Pardon?
Like, is the audience, can you hear the audience? Or is it just my voice?
No, everybody agrees, I think. I mean, if you do the experiment properly, that is to say, you hold the band against your forehead and pull it rapidly, you'll feel a bit of heat on your forehead. And when you release it, you'll feel some coldness. So the connection, people ask, why is heat connected to disorder? This experiment clearly brings it out. Okay. So can I go
So
on?
the audience have tried it. You can proceed, sir.
Okay. So here is an example of disorder. This is a slinky. And up here, you can see it's close to the hand. This part of the slinky is terribly disordered. This part is terribly ordered. And that's exactly what I mean by disorder. This is at a macroscopic scale, but a similar thing happens at a molecular scale also. That's what you see with the rubber bands. Now, closed systems have a fixed total energy. The energy will tend to dissipate into heat, and the final state will maximize entropy for a given energy. And this was the remark made by the person who came up for the question, to answer my question. This is the thermal state, and it has a temperature, and we cannot extract work from a single temperature. However, we can extract work from two thermal systems at different temperatures, and I'll show you a demonstration of that. Here is an engine. What this is that on the tray below, you can see I've kept a steel container with some ice in it and some foil. And the wheel here is going to turn because of the temperature difference between room temperature and the ice. So let me just run this engine. There's no battery in this engine. It's running entirely on the difference between the two temperatures, the temperature of the room and the temperature of the ice, which is below it. Now I move the engine away from the ice, and there's a foil there for conductivity. And you can see that the engine will start slowing down because the source of the energy has gone away. Let's give it a few minutes. You'll see it runs, but it slows down and eventually it stops. Now I'm removing the foil to show that there is ice under the foil. And that's the ice that was causing the temperature difference between the room and the ice. And you can see that the engine is now slowing down and completely coming to a halt. Yeah, so that's stopped now. So this is an example of, it's like a Carnot engine, except it's moving at finite speed. Now, black holes now produce a big conundrum for the laws of thermodynamics. We can think of black holes as entropy sinks. If I have a black hole, I can throw some disorder into it and decrease the disorder in the universe. Whereas the second law of thermodynamics is telling me that the disorder in the universe always increases. So this would violate the second law of thermodynamics. To avoid this violation, we must say that black holes also have an entropy. So when we throw entropy into a black hole, the entropy of the black hole must be increasing. Now, what has been found by researchers is that the entropy of a black hole is geometric. Just like we talked about relativity being geometry, the entropy of a black hole is also geometric. It's proportional to the area of the black hole. It has been shown that the total area of black holes always increases. This was work by Hawking, quite remarkable work. We conclude that black holes are thermodynamic objects, and so they must have a temperature. They have an entropy, so they must have a temperature also. Like all hot bodies, they must radiate energy. Now, Hawking showed that in quantum physics, black holes are not black, but they glow with a very small temperature. If you put something on a stove, for example, it can become red hot and radiate. So any object with a temperature radiates. In fact, your body temperature also radiates in the infrared. Your head actually puts out a lot of infrared radiation. When your brain is working, you create a lot of heat, and that makes your head radiate, and which is why you can be seen on an infrared camera. But Hawking showed that black holes also radiate with a very small temperature, and that's known as Hawking radiation. This was a discovery in the 1970s, before most of you were born. Hawking's striking insight was that in quantum theory, black holes radiate and they have a temperature. And this temperature is very tiny. It's about 10 to the minus, well, for a solar mass black hole, it's a very tiny temperature, far colder than any temperature you have come across. Now, this led to deep connections between gravitation and thermodynamics, and this is the subject of current research. So my conclusion is, well, black holes are macroscopic objects with a microscopic description. Thus, we can describe them in terms of Einstein's geometry of curved space-time. Current research focuses on the following question: is information really lost in black holes? If you throw something into a black hole, do you really lose that information? Now, this seems to be suggested by Hawking's work, that you can put information into a black hole and what comes out is only thermal radiation, which has no information in it. And it produces a conflict with quantum theory. Where are the degrees of freedom responsible for black hole entropy? Are they stuck at the boundary? Is there new physics beyond general relativity? And it's widely believed that this new physics is a subject called quantum gravity, which does not yet exist. Or is it some kind of unified theory? Let me just close. I've reached 7 o'clock, which is the time allowed. Let me close by saying that science is a combination of imagination and skepticism. Imagination is what let Einstein conceive of curved geometry as describing gravitation. But there's also a lot of skepticism necessary. You must not believe everything you hear, everything which is told to you. And it's a combination of imagination and skepticism that causes science to grow and for us to understand the universe better. So let me just stop here and thank you all for your attention. I think I've finished in time. It's just about 7 o'clock now. I started at 6. Thanks for your attention, and I'll be welcome questions about what I've said.
If anyone has any questions, you can come up to the stage. Any questions? No, sir. We have. Oh, we have one question. Uh,
Yeah, please come up to the stage and ask the question.
So, so for Hawking radiation, so where is the antiparticle and particle pair formed? Like, is it at the singularity, or is it at in between the singularity or the event horizon, or at the event horizon?
Yeah,
Or
it is
don't know.
at the event horizon, what happens is that this is a simple picture of Hawking's derivation, mathematical derivation. You have always in the vacuum of quantum physics, particles and antiparticles, which keep coming out and popping back
Going,
into the
yeah.
vacuum. So what you have is at the event horizon, if you have a particle-antiparticle pair, and one of them escapes outside, and the other one falls into the black hole, that is
Okay.
Hawking radiation. And
Okay, so
this
it's forming everywhere, but only at event horizon is it able to escape.
That's correct. Yeah. So, and in
Okay.
fact, even there, it's a tunneling process. It's a quantum mechanical tunneling process that lets it escape.
Okay. Okay. Makes sense. Okay. Thank you, sir.
Very, very good question. And actually, let me just expand on that answer. The area of a black hole is proportional to the square of the mass of the black hole, and the temperature is proportional to the inverse of the mass. So for a solar mass black hole, you have a very small temperature, but for a small black hole, you would have a very large temperature. Such black holes have not been seen, but the effect is absolutely there theoretically, and one day we can hope to see it in experiments which are done in laboratories where they make analog black holes which use sound instead of light.
Okay.
Thank you for the question.
Thank you, sir.
We'll be providing refreshments shortly, so I'll request the audience to remain. So we have one more question.
Yes.
That's a very nice talk with full demos. So I was wondering about this falling water bottle demonstration.
Yes.
So
Yeah.
if you make the hole at the bottom of the water bottle instead of at the side, will it
Yes.
still stop
Yes.
the
Yes.
water?
You can try it and you can convince
Yeah, I'm
yourself.
going to try it.
Yeah. Yeah. And
Okay.
actually, there's an important point here. The important point is that the bottle and the water fall at the same rate. That's why the thing does not leak. Suppose the bottle does not fall and water falls. That's the usual situation. When you hold the bottle in your hand, you're stopping the bottle from falling and the water is still falling. So it'll fall down. But when both of them fall at the same rate, you will not see a leak. And if the water falls slower than the bottle, if suppose the bottle falls very fast and the water does not fall for some reason, then the leak will be upwards. The water will be falling upwards relative to the bottle.
I see.
So Galileo's experiment showing that all matter falls at the same rate is an important experimental input into this demonstration.
Yeah. Okay. Thank you.
I'm sure you'll try it out and you can take a
Yeah,
video.
yeah, I'm going to try it.
Yeah, take a video in slow motion with a camera and send it to me. All right.
Sure.
What's your name?
So my name is Shilaritya.
Okay, Sheila, I look forward to getting a video from you. You'll learn a
Yeah.
lot from doing the experiment.
Yes, thank you.
Yeah.
Do we have any more questions? So we have no more questions.
Okay,
And
thank you very
the
much.
talk was very interactive and the audience enjoyed it a lot. Uh, Thank you, sir. And do you have any resources so that we can read up more about what you discussed today?
Uh, yes,
Could you suggest
actually, if
some
you follow,
resources?
yeah, if you, well, firstly, I want to thank the audience for your attention and your questions and also for the lively interaction. I'm very happy with all that. But about other resources, you should check out the ICT's website. We have these popular talks called Copy with Curiosity, which deal with a range of subjects, and they're online talks. So you can get some ideas for physics in general. And also, there are many topics in physics which are covered there, including black holes. And that's one resource I can suggest. There are also many sites on the internet. For example, there is a site called Physics Girl, where she talks about many interesting physics demos. And there's another site called Veritasium on YouTube. They're all excellent communicators. They have the resources to make much better videos than I have been able to make. So I can recommend that you follow all these resources.
Sure, sir. We'll look up these resources. If you have anything to share to the audience, you can speak, sir.
Okay. So thank you very much. And all the best.
Thank you so much.
Bye.
Bye, sir. Thank you.
Recording.